Great. OK, great. So we have an in-person physical talk now. SwitchV, SDN switch validation with P4. Stefan Smolko is a senior software engineer in Google's network infrastructure group, and he's open to internships, jobs, and collaborations. Over to you.
Thank you very much. Seems like the microphone is working great. Yeah, so I'm really excited to tell you about this new approach to switch validation that we've been using at Google for the last couple of years. This is joint work with a handful of colleagues and ex-colleagues at Google, as well as collaborators at Brown and Harvard that started from internships, actually. So come intern with us. All right, so many of you will know the P4 programming language. The idea is that you write a program, and you can then execute it on a programmable ASIC, and it will tell the ASIC exactly how to manipulate packets in the data plane. What you might not know is that the way we use P4 at Google is very different from that original use case. We actually write programs that match precisely what the fixed function ASIC does, a fixed function ASIC that you cannot change with a program. And so we write our program to tailor it exactly to a fixed function ASIC. So you might be wondering, why would anyone do such a crazy thing? Please bear with me. That's what this talk is all about. So before we get there, let's travel back in time about 4 years or so, when engineers at Google started thinking about what our next generation SDN switch for the data center should look like. We had a couple of goals in mind. Obviously, the new switch would have to be much faster than previous switches, and so we would be building on the newest available hardware, new ASIC, new optics. But we also wanted the switch stack, the software, to be open source and industry aligned, to make it easier for us to collaborate with external collaborators, to work together with them. Additionally, we wanted the switch to be silicon independent, so we could use ASICs from different vendors. And also, further down the route, we wanted to be able to use programmable ASICs with the same switch stack as well. And then, in order to take advantage of capabilities of these programmable ASICs, we wanted to start using a new SDN API, P4 runtime instead of OpenFlow, and integrate things with our existing SDN controller, Orion, which you may have heard about before. And then finally, to actually deliver value to the company, we would have to deliver a data center fabric based on this new switch. So when we started looking at the timeline for this kind of project, both planning, design, development, quickly became clear that this is a very ambitious project. So ideally, you would do this sort of sequentially in order of dependencies. But obviously, we don't have time for that in industry, right? And so what we were going for was this very, very ambitious timeline where you essentially design things all at the same time and develop them, which means that when you start building your switch, you don't even know the final specification of the hardware quite yet. So in general, you don't know quite the specifications of the layers below you, and you don't know exactly the final requirements of the layers above you. They all change as you go. So very, very challenging project. And the main headache we had here is, how do we pull this off? And yet, after 3 years, we deliver a production-grade data center that is at least as reliable as current generation, because otherwise, this would just not go into production, right? So the main problem we're faced with here is this inherent tension between feature velocity and reliability. We kind of understand how to build very reliable switches. We just write a ton of tests against the final specification of the switch, and we can do this quite well. The only problem with that is, well, first of all, we don't even know the final specification when we start developing. But also, if you've written all these tests and now your specification changes, you have a ton of work to do to update those tests. And every time a new feature comes, again, you have to write new tests. So this really slows you down. At the other end of the spectrum, we could just not bother with testing at all, and then sure enough, we can move really fast. But of course, our switch is going to end up not being reliable. And so in general, with manual testing, you can trade off between these two extreme points. But unfortunately, that's just not good enough, right? So we really need to be in this top right corner there to pull off a project like this. And we didn't really know how to go about that. Surely you could hire more engineers, but that costs a lot of money. And no matter how many engineers you hire, there's still some latencies if you have humans write tests or update tests as your specification changes. So this was just not good enough. So what we're asking for here is almost too much to ask, maybe. We kind of want a comprehensive set of tests to appear magically every time we have a new or modified feature. But it turns out we can kind of pull that off. And let me show you how. So the idea is to use automated testing somehow. So here now is our real switch stack. This is what it looks like. There's a ton of complexity there. We have the hardware at the bottom, an ASIC and a CPU. We run a whole Linux on top of that. Then you have 2 layers of drivers and abstraction layers to expose the hardware in a vendor-agnostic way. And then you have 3 more layers on top of that. That's our pin switch stack, built on Sonic, which basically gives you a database abstraction of the switch and also gives you a gRPC server, a P4 runtime server, so you can remote control the switch. So a ton of complexity here, and we're making changes across all these layers, millions of lines of code. So how do you go about automatically testing this? Well, if we take a step back, forget about all this complexity, and we focus on what are the key things we want the switch to do. And what you get to is this. There's really just 2 main things we care about from an end-to-end perspective at the end of the day. 1, we want our switch to forward packets, right? That's the data plane. And 2, we want to be able to control how the switch forwards packets via a control plane API. And we can forget about all the other details from an end-to-end perspective. Conveniently, there's already a programming language that allows you to specify precisely those 2 things. And that's the P4 programming language. And so what we do is we forgot all the details, and we model only the data plane behavior of our switch and its control plane API in a compact P4 program. Now we're down to about 1,000 lines of code or so. And at this point, we have almost solved the problem, because this kind of program is actually very amenable to automated testing, right? So again, we now have around 1,000 lines of code or so. Moreover, this code is actually written in a very, very restricted language, right? P4 is not a powerful language. It doesn't have recursion. It doesn't have loops. It's basically straight-line code, very easy to analyze. So we can use all these static analysis tools, symbolic execution, and so on. And in particular, there's a ton of great work in this space already. Tons of existing tools. We just heard about one, MISA, and there's P4 Test Gen, ATPG, many, many others. And we can start to leverage them. So the final puzzle piece here is to understand that once we can test our P4 program, that means we can also test the switch. Because the P4 program and the switch, in terms of their APIs, the data plane and the control plane API, they're the same. And so what we're going to do is we're going to take these tests for the P4 program, and we're going to run them on both the switch, the real switch, as well as on a P4 simulator of the program. And then we're going to compare the behavior of the model and the real switch. And whenever there's a difference, we're going to flag it as a bug. All right, so in summary, SwitchV is a framework for automatically generating tests to validate switch conforms to a given P4 model. And there's 2 parts of it. P4 Fuzzer is a fuzzing tool, and it's focused on testing the control plane API. And so it does that by generating valid and invalid API requests and then checking that the switch handles them in a manner that is P4 runtime standard compliant. And then on the data plane side, we have P4 symbolic. It uses symbolic execution to generate test packets automatically, and then verifies that the switch forwards them as the P4 model would predict. At this point, I want to stress that our paper has some interesting insights about these tools, and I'd encourage you to look at them. But it's kind of not the main point. Again, there's a ton of existing work in this space. It's really cool. And the main takeaway here is that we can leverage all this technology to test fixed function ASICs that were never built with P4 in mind. So that's really the key idea of this work. Nonetheless, let's take a quick deep dive into how data plane testing works concretely, so you can see where the rubber hits the road. So here's what we do. The idea is as follows. We start with a switch under test and a P4 simulator of our model. And we're going to compare their behaviors. We do that by first installing some set of table entries. In practice, we use production snapshots, so past table entries that we've used in production that are representative of what we want our switches to do. And we install them on both the P4 model, or the P4 simulator, BMV2, and the real switch. And then we start sending packets to the real switch and observing its output packets. And we send those same packets to the P4 simulator and get expected output packets. And then we verify if they do the same thing. If they don't do the same thing, something is wrong. And we look closer. Now, how do we choose these input packets? The effectiveness of this approach relies crucially on your choice of input packets here. Ideally, you would generate all possible input packets, but obviously, we've talked about header spaces in previous talks. It's way too many packets, right? So we need to choose them cleverly. And the way you do that is based on symbolic execution. And we use P4 symbolic to do it. So that's where sort of all the brains of this approach go into. So let me show you how we do it at Google. Again, we use symbolic execution. So our strategy is to hit every table entry on the switch with at least one test packet. So here we have an example table entry. So now to generate a packet, we basically walk over the program and collect constraints. So any packet that wants to hit this table entry needs to have VRF42, and its destination IP needs to lie in this given range, right? But there's additional constraints. We also want to make sure that we don't hit a higher priority table entry. And so we also need a constraint that says that we don't hit this other entry with a higher priority. That's not quite all yet. VRF is a metadata field. It's not actually part of the packet. And it's being set by a previous table earlier in the switch pipeline. And so we also need to make sure that that we hit some kind of table entry earlier that would set this VIF value to 42. And so similarly, we collect constraints for that table as well. And so we end up with a big formula. And once we're done with that, we just hand it to an off-the-shelf SAT solver. We let it do its work, and it gives us back the packet we're looking for. So pretty much standard techniques. All right, so let me talk a little bit about how this works in practice. Like I said, we've been using this for over 2 years now. So the first question you might wonder is, like, does this actually find relevant bugs? And the answer is yes, a ton of them. So we found over 100 bugs. And for the large majority of them, these are very relevant bugs, and they get resolved quickly. And this is really a very conservative approximation. We're not counting bugs that were prevented, that never made it into the code, because developers were using our tools before even submitting their code. So the next thing you might wonder is, like, where do we find bugs? Well, we find bugs across all layers of the switch. In the previous talk, they talked about code bugs and non-code bugs. We can handle all of those. So we found bugs including in the hardware. And if you want to see more examples, please take a look at the paper. One thing I want to point out here is that our approach uses a P4 model. So obviously, we can also make mistakes when we model our switch. And so indeed, we find 10% of our bugs are actually not switch bugs. They're model bugs. But what I want to point out here is that our approach is resilient to this. This is not a big problem in practice. When we find a discrepancy between the switch and the model, either way, we go and fix it. And I think the probability that we would make the exact same mistake in the real switch and the model is very low. Two sort of independent, low probability events coming together. So we're not very concerned about this. Finally, you might ask, are we missing any bugs? And I want to be clear, we don't have the final answer on that yet. But we do have one very encouraging data point. So we recently went through a more sort of standard, old-school testing phase, where when your switch is almost ready for production, you basically build a big traditional data center fabric based on that new switch, and you run sort of traditional testing. You run a bunch of workflows, and you see if anything goes wrong. And sure enough, a ton of things go wrong when you do that. But none of the bugs we found, 0, were in the forwarding plane of the tests of the switch. So that's a very encouraging data point. So to wrap up, if you wanted to summarize the key idea of this talk in 3 words, and you like buzzwords, I would call this specifications as code. So the main idea here is that we write a specification for our switch in a programming language. And that means that other code, other tools can read the specification and automatically generate tests based on that specification. And so this means that our tests evolve effortlessly with the specification. Whenever we change the specification, we immediately have new tests to check that the switch behaves according to this new specification. And so we really get these 3 things: cost effectiveness, reliability, and feature velocity. So with that, thank you, and looking forward to your questions.
One microphone in the middle, if you can. Can one of you? Yeah. I think if there's anybody else, you might as well stand up already. Yes.
Hi, thank you very much. Abu from Huawei. I like this talk a lot, mainly because of the reason that why P4 was developed, right? They always said that you can program the fix function ASIC, but then we found out that it's for programmable ASICs. So what was so you have ran this on the fix function ASIC, is that correct?
Correct.
So what were the ASICs that you tried, if I may ask?
Unfortunately, I cannot tell you this. Yeah, I cannot say anything about that, unfortunately. I don't think I can say anything useful at all. I'm looking at Jonathan, one of my co-authors. No, sorry.
That's fine. At least it was a quick question.
OK.
Thanks.
Thanks.
Microphone there. If anybody wants to ask a question after, ask for a microphone already. Yeah.
Hey, thanks for the great talk, Laurent from ETH. I was wondering, perhaps it's a question about the thing that you don't test. So I was wondering about non-functional requirements, like the performance, for instance. So you receive a rule install instruction from this northbound API. Then it takes time, of course, for this rule to be downloaded into the ASICs, for instance. And you really have to cross the entire complexity of your software stack. So it would seem that for that, you really need to do these tests the old school way. So I guess it's really then complementary approach, or do you have also like thoughts about that?
Yeah, so first of all, I 100% agree. So we cannot test everything. This is really specific to the forwarding plane correctness. And yes, we still need traditional testing. So you mentioned one, performance. We're actually struggling with that right now. So yes, that's an issue. There's also like QS, things like that we didn't consider here, and there's still issues. So yeah, this is sort of a space where this kind of approach works very, very well. It doesn't work everywhere. And we're thinking about ways we could extend this to other parts of the switch. But I think at the end of the day, it's not going to work for all parts of the switch. So traditional testing still has a place in this, for sure.
I don't use Windows, so I don't know. Great. Any other questions while we set up? Domishai? Going once? Going twice? OK, let's thank the speaker one more time. Thank you. Thank you, Stefan. Great.